Hello, everyone. So I wanted to address a few things about this current homework. So let me just digress a little bit and talk about a few confusions that came up. Confusion number one is it's concerning the Compton scattering problem. So let me share a screen. Let's see, we'll stop. Do you want to continue? Yes. So let me share a screen. I want to emphasize that yesterday, when we talked about Compton scattering, so this is a picture from your textbook, I jumped right, I said a few words. Words are important. And the words were that we treat the incoming photon as a particle. Well, and then we just use momentum and energy conservation, okay? With just funny momentum and energy formulas. Normally, the momentum is given by gamma mu, and energy is gamma mc squared. But for massless particle, I discussed massless particles, well, there has to be other relationships, okay? They come from outside of relativity, and that is the energy equals HF, right? Or HC over lambda, and the momentum is H over lambda. After that, we just treat it like a regular collision. And if we do that, if we really take it seriously as a particle with these funny energy and momentum formulas, out pops this expression. And I didn't go through the details of how it's derived. And again, I said we treat this as a regular collision. And what happens in regular collisions? You have to conserve the momentum. Momentum is a vector. So it has X component, Y component, and there's also energy. So here are the three equations. So here's conservation of X component, here's conservation of Y component, here's conservation of energy. Once you have used this expression right here, which relates a lambda and a lambda prime, incoming, outgoing wavelength. So from there, you can get the angle of the outgoing photon. But what about the angle of the outgoing particle and velocity of the outgoing particle? I mean, electron, right? So how do you get this angle and this velocity? Well, again, you have two unknowns, so you need two equations. For instance, you could use these ones, the momentum ones. And then you just have to be a good sport at solving this, like you would solve any linear equations. Well, how do you do that? Well, you could, for example, move this thing to the other side and divide one equation by the other to eliminate gamma mu, because there's a common factor, gamma mu. And then you would have something like cotangent or tangent of phi in terms of everything else that you know. Again, it's a regular collision. It's a relativistic collision, but it's a collision of two particles where one of them is an electron, what you think of as particle, and the other is a photon, which is a funny particle. Its energy and momentum are related to its wavelength. Okay, so that's what you need for that Compton scattering problem. Yes, I skipped these. I did skip these, but this is in your textbook. You're expected to read the textbook. Another example, I think there was another question. Oh yeah, so there was a question. Let me pause for a second. I hope you can see the sketchpad. So another question was, let me read the question. It was concerning the, you were given a table, yeah. So you were given a table of, you're given a wavelength of light and the stopping potential. Now, what is a stopping potential? Well, I explained what that is, but I talked about it, but I didn't go into details, right? So again, you have electrons being, launched from this piece of metal, and what you could do is you could apply a battery. Now, what does a battery do? It applies a potential difference, right? So electrons go in the direction. If you don't have a potential difference, the electron will just coast along, hit this piece of metal, get absorbed, and then you can put an ammeter here and measure the current. How do you stop the electrons? Now, protons go in the direction of the field, electrons go in the opposite direction. So you could apply electric field. How do you apply electric field? By applying a voltage difference, right? So that's where the battery comes in. Now, if the electrons are moving in the field, well, what happens to the electrons? they will slow down. Energetically, their kinetic energy, the initial kinetic energy, gets exchanged for potential energy. And at some point, the kinetic energy will be zero. That's called a turning point. Electron comes here and turns around. Now, kinetic and potential energies get exchanged. Their sum is conserved, but the energy gets exchanged. Well, so okay, so how do you measure from that the initial kinetic energy, right? So you know that kinetic energy initial becomes equal to potential energy final. Really what it is kinetic energy, really what it is, it's this, right? So kinetic energy final minus kinetic energy initial, this is 0, equals potential energy final minus potential energy initial. So this is change in potential energy. Now, what is the change in potential energy? Change in what kind of potential energy? Electrostatic, electric potential energy. And if I apply a voltage difference between the two plates, how do you relate potential energy to potential? Well, you should know this, right? Change in potential energy equals charge times the change in the voltage difference. The question is, what's the voltage difference between the starting point and the point where they turn around? We know the voltage difference between the two plates, but what's the voltage difference between this point and this point? I mean, maybe you could say, well, the potential grows linearly, it's a parallel plate capacitor. But what you could do is you could tune down the voltage so the electrons stop right here, right before getting absorbed. And then the potential difference between this point and this point is just the potential difference between plates. So, long story short, if you know potential difference between the plates such that electrons barely get here, that's called stopping potential, right? So stopping potential, that's what they mean by stopping potential. It's a potential difference that stops electrons right before they get to the other plate. So then that means the electrons go all the way through this whole potential difference in your battery, 9 volts, 100 volts, whatever. And so then you know the difference in potential energy. If you know the difference in potential energy, you can relate that to the difference in kinetic energy. See, these things that you learn in Phys 3, they're not just for jumping through hoops, okay? They're very practical, concrete things. I think I'm preaching to the choir here because most of you are electrical engineers, but if you weren't electrical engineers, you probably think that this is all kind of just like to make your life miserable. No, it's not. These are actually very practical things, right? You're shooting a bunch of particles. You want to know their kinetic energy, right? You cannot see them. You can't film them. How do you do that? This is the technique to do that. You see. And there was also another question. The question was, if you have a brick, like 1 kilogram of mass, you completely convert it to energy. Compare that energy to the energy that you need to get Empire State Building into orbit. Now, here's the Earth, and here's the low Earth orbit. You have to understand that low Earth orbit, it's low Earth. It's only 100 kilometers above the Earth's surface, whereas the Earth's radius is like, what's the Earth's radius? It's like 6,300 kilometers. I don't remember. Look it up. And so therefore, as far as this problem is concerned, you may as well just imagine that the Empire State Building is in the orbit right at RE, like a cruise missile that's just hovering over the Earth, okay? You can convince yourself that if you do a more correct calculation, that would involve a little trade-off in the kinetic energy into a potential energy, gravitational potential energy. You will see that the prediction would actually be not very different. It would actually be very similar, right? So imagine that you can ignore the 100 kilometers, and then what would be the kinetic energy of the Empire State Building? right? Well, to know the kinetic energy, you have to know the velocity. Or you know the velocity of something orbiting Earth at a given radius, right? So that's, again, that's your phys1 here, right? So if something is going in a circle, right? So if something is going in a circle, I'm just scratching my nose, I'm not picking it. Something is going in a circle, you have a centripetal acceleration, which is v squared over r. And what's the cause of that acceleration? Well, that's on the one hand, that's general. On the other hand, this is basically g. Again, a g 100 kilometers from the surface is very, very similar to g at the surface, actually. That's interesting. It's, the reason you're weightless up there is because you're in state of free fall, okay? When you're in free fall, you don't feel gravity. But it's not because the Earth's pull is significantly weaker. It's not. It's only like about 1% change in the radius from the center of the Earth. Okay, so from here you can get V, and if you know V, you can get kinetic energy. Okay, it's quite a large value by human standards, by conventional standards, but you will see that you can actually get more than enough from just converting 1 kilogram of mass to other forms of energy. You know, mass energy to other forms of energy. Look, guys, the moral of the story is, why are you solving problems? Well, you might say, well, just to jump through, because we just want to make you jump through hoops on the way to the diploma. No, that's not the reason you're solving problems. You're solving problems because problems are supposed to teach you something, okay? And so what I really want you to do is, after you're done solving a problem, you just kind of step back and kind of stare at it and go, okay? And the here, what's the moment? The moment is that you are supposed to realize that mass energy is an unbelievable amount of energy, okay? One brick, if you completely convert mass energy of one brick, or mass of one brick, into other forms of energy, you know, energy of light, and so on, you get plenty. And so that's really, that's kind of how nuclear energy works. And in nuclear energy, you don't convert all mass into energy. Convert a tiny fraction of mass into energy. In chemical reactions, you convert even much smaller fraction of mass into energy, hardly any. Mass hardly changes in chemical reactions. It does, just like I said, hot potato is heavier than a cold potato. Compressed spring is heavier than an uncompressed spring, but that's a minute change. Okay, when you convert, when you extract energy in nuclear reactions, that's a little bit more of a change. And then if you really convert, you can really convert all of the mass energy to other forms of energy. That's unbelievable amount of energy. And the reason it's so unbelievable is because of the c-squared. The c-squared is really large. Okay, so that's what I wanted to say. I think this is enough of a spiel in its own right, that I think I'm going to stop here. I'm going to start the actual lecture in a separate video, and it's probably going to be just one video. Today, I just want to talk about the double slit experiment, the classic canonical double slit experiment that basically contains the essence of quantum mechanics. So we're going to start discussing that today. We're going to discuss it more on Monday in the context of electrons. And so I think it deserves a separate video. Okay, so I'll see you in a separate video.